So if we're dealing with a simple rational function that's linear polynomial divided by linear polynomial, we can always rewrite those. We have a trick. We can always rewrite those so they look like transformations of the parent function 1 over x. Right? So we could do, we know that the parent function f of x equals 1 over x. We know what that looks like, right? That's going to be a function that has vertical and horizontal asymptotes, a vertical asymptote through the origin and a horizontal asymptote through the origin. And we all know what that means if I say an asymptote, right? A line that kind of guides the behavior of the function. It's going to approach it but never touch it, kind of a thing, right? And then it goes through the point over 1, up 1. So it does that. And it goes through the point -1, -1 also. So it looks like that, right? So we can take a parent function like this and we can move it around. We can transform it by doing something like a times 1 over x minus h plus k, right? Where h and k are going to be the coordinates. They end up being the coordinates of that center point where the asymptotes cross. And a tells us what we've done to this point. Normally we go over 1 and up 1. If it's negative, it means we've reflected it. If it's bigger than 1, we stretch it. If it's less than 1, we compress it, right? But we can just turn this into a function like that. So we can see what a, h, and k are. We can get a sketch of the graph, right? So how did we do that, though? How did we do that? How did we get from there to there? What was the process? Because this looks different, right? You can't look up there and say what a, h, and k are, right? How do we turn that into something like that? What do you think, Justin? What'd you do?
You have to divide, like, or find a common denominator. Or was that another one?
Yeah, it's not, I mean, we don't really need a common denominator, but we need to divide this out.
Oh, you got, your,
Okay, yeah.
You got x equals 1, and then you gotta do the division.
Okay, good. We're gonna divide out this quotient. And this goes back to section 6.5 is when we first talked about this, right? So we can either use long division, polynomial long division if we need to, or we can take a shortcut and use synthetic division, right? If we use let's do one with long division. It really doesn't take very long to do for these easy ones. If I want to divide this out, the denominator goes out front, right? So x minus 1 goes out in front of the division, whatever you call that, the division bracket. And then the x plus 3, the numerator goes inside. And how do we do that? How did I find out what the first number in my answer, or the first part of my answer was? What did I do? I divided. I just divided the leading term inside, so in the numerator, by the leading term outside. So x over x equals what? 1. So 1's the first part. Another way of saying that is I could just ask the question, how many times does the leading term outside divide into the leading term inside? In other words, x times what equals x? Well, 1, right? And then once we get a number up here, we always just distributed that through, right? So x, or 1 times x is x, 1 times -1 is -1, and we subtracted the whole thing, right? So x minus x canceled. 3 minus -1 was what? 4. So that was our remainder, right? And so then we took our original function and we just rewrote it as 1, right, plus our remainder of 4 over the denominator. Okay, that's getting closer. We want it to look like this though, right? So then what do we do? How do we get that to look like that? Where does the 1 go? It's by itself. It's the end, it's K, isn't it? Yeah, that goes at the end, so we're gonna flip that around, and we'll write this as something plus 1, and here's the something that we're adding to 1. Well, we want that to look like A times 1 over x minus h. So I've got my x minus 1 on the bottom. If I just factor out that 4 from the numerator, then I'm leaving behind a 1, right? So I'll take the 4, and I'll pull the 4 out front like that, and we got it, right? Yeah.
How did you get 4? Wouldn't it be 2? Like,
No, because I've got 3 minus negative 1, right? Anyway, I always want to put this in parentheses and subtract each term, okay? So then we end up with, something like this. Now, this is helpful, right? So what are the values here? Gage, tell me something that's going on here. Tell me a value of A or H or K or something. A is 4, okay? Good, and say it again. K is 1. And what's the other thing we see up there? H is 1, good, because it's what's being subtracted. Okay, so if we wanted to graph this then, this one's going to be a little bit different, right? We've taken this parent graph, and we've moved this point over to HK, so we moved it over to 1, 1. Everybody see that? Okay, so if we made a graph of this one, so that's where that center point is going to be, where the asymptotes cross, right? And then A is 4, so instead of just going over 1 and up 1, we're going to go over 1 and up 4, right? So there's going to be a point, and the function's going to do that. And if we went backwards 1, instead of going down 1, we're going to go down 4. So it's also going to go through that point. Okay. So the 4 just takes the function and pulls it further away from the asymptotes a little bit, right? Okay? All right, so now our goal is, can we do the same thing without having to go through that whole process, right? Is there another way we can do this? Could we just look at the rational function and say, okay, we could get a sketch of this without having to divide it out? Because we're going to start looking at some other functions here pretty quick, like that, where it doesn't work anymore. Because now the top is more complicated. It's not linear. And so if I divide that out, it's not going to look like a transformation of 1 over x. So that trick goes away. It's useful when we can use it, but it doesn't always work. All right? So let's think about this picture that we got. Our picture looks like this, right? It's got asymptotes at, let me draw this a little better. We can see this a little better. So our picture looks like this. So we had a vertical asymptote at 1, didn't we? And a horizontal asymptote at 1, and they crossed at the point 1, 1, right? And if we went back, let's see, if we went over 1, we went up by 4, right? So it looked like that, and if we went backwards 1, we went down by 4. So we got a point there. So it looked like that. So where was our vertical asymptote? At x equals where? X equals 1, right? Good, so that's our vertical asymptote right here. Okay, could we have predicted that from the function? How? We could. How do you think? What about this rational function is telling us vertical asymptote at x equals 1? You can be wrong. It's all right. Just throw something out there. What do you think? Yeah, the bottom, right? The 0 of the denominator is 1. Everybody agree that's the value of x that makes the denominator 0? Okay, let's think back. Let's think back to some discussions we had earlier about domains, a function. So the domain is just all the values of x, right, for a function. What if we took an easier function? What if we took something like a really easy one? Like let's take f of x equals the line 2x. What's the domain for that function? The domain, the set of values, x values. Are there any values that wouldn't work for x? It's all reals, isn't it? Right? If I graph this line, it's just through the origin with a slope of 2, and it goes forever in either direction, doesn't it? Right? And so there's no x value I couldn't put into this function. It's going to give me back a y value. What about this one, though? Is there an x value that I can't input into the function, and why? 0, if I put, let's see, if I put 0 in, what do I get back? If I put 0 in, I'm getting back 0 plus 3, so I get 3 on top and 0 minus 1, negative 1 on the bottom. So I get back the point negative 3. So that's telling me that I've got the ordered pair 0, negative 3. But that is it works. I get a point back when I do that. Well, yeah, 1. How come 1 doesn't work? Because I got to divide by 0. That's one of our 2 rules, isn't it? We said there's only 2 things you can't do for real numbers. We can't divide by 0, and we can't take a square root or any even root of 0. We can't. What's the square root of 0? 0. Square root of 1 is just 1, but I can't take square roots of certain kinds of numbers if I want to get back a real number answer. Negative numbers, right? So for real numbers, I can't take an even root of a negative number, and I can't divide by 0, right? So, yeah, if we look at this, because of the denominator, right, we would have to say that our domain is going to be all x values except x cannot equal 1, because that makes the bottom 0. Well, what's happening at x equals 1? That is, we're getting a vertical asymptote, right? The function can get as close as we want to the vertical asymptote, but it can never get there. It can never have an x value of 1. The closer you get to x equals 1, the further down you're going to be along the asymptote, or up you're going to be along the asymptote. But it's like an infinite barrier. If an ant is crawling along this function, it can never cross that barrier. It's going to go, as it goes from left to right along the function towards 1, it's going to go down infinitely far, but it's never going to get to x equals 1, right? Okay? So let's see if we can come up with a pattern then. Let's just look at some functions here and see if we can come up with a pattern. Anybody want to make a prediction if we graph this about what we're going to see? Look at that function. See if you can tell me some things that are going to happen there maybe. Okay, where do you think we're going to have a vertical asymptote? Negative 1. Okay, let's see it. Let's see what happens. Come on. So let's try this. So on the top, we're going to have x plus 5 times x minus 1. All divided by x plus 1. What do you know? Okay, if we look at that, if we zoom out a little bit, what's it look like? Where is there a vertical asymptote? What do you think? Jessica, where's there a vertical asymptote? Will you help me out here? Oh, I guess it has. Oh, well, mass for a different period. Ariel, tell me, where's their vertical asymptote? Where does the function? Where does it run into a vertical barrier? You know, where it just.
0.
It looks like 0. Kind of looks like 0. But if I zoom in a little bit, where is it?
1.
Looks like 1, isn't it? Yeah, right at 1. And that's because that's the 0 of the bottom. Let's graph the function. I'm going to make this f of x. Okay, let's do 2 things. Let's graph the vertical line y equals negative, or x equals negative 1. There we go. Okay, so if I graph that function, can I pick a different color? I don't know how to do that. Anyway, look what happens. If I zoom out, watch what happens here. The black line ends up being the vertical asymptote, doesn't it? Everybody see that? Okay, there's another one going on there too. There's another asymptote. If we go really far out, you can see that the purple function, it's also got an asymptote along this other line. We'll call that a slant asymptote, but we're not gonna, I don't want to deal with that today, right? But really far out, the function just looks like the asymptotes. Right? And that's the way asymptotes behave. If I turn off the black function, there it is, right? Okay, what's going on? So we were right. We made an estimate that we anticipated we were going to get a value, or we're going to get a vertical asymptote at -1. What is the value of the function at -1? Let's see. If I take f of -1, the function's undefined, right? It's not going to give me back any result because that's not part of the domain. Okay, what's happening at the zeros of the top? Look at the numerator here. So what are the zeros of the numerator? -5 and 1. Okay, good. So if we break this into parts, numerator and denominator. The zeros of the numerator are at x equals -5, and where else? So -5 makes the top 0. What else does?
1.
Okay. And then the denominator, you already told me that the 0 is at x equals -1. All right. Okay, so what's going to happen if I go to my function and I put in a value of -5? What am I going to get back for a y value? What do you think? There's my function at -5. Well, let's try it. If I put in -5, I would get 0 times -6, right? So what's the top of the fraction? What's 0 times -6? 0. On the bottom, I'd get -5 plus 1 is -4. What's 0 divided by -4? 0. Well, let's see what happens. If I plug in -5, I get back a y value of 0, right? And there it is right there, isn't it? Right? So that's just an x-intercept, right? That's when we say a 0 of a function, we just mean an x-intercept, right? That's where the y value is 0. How about right there? Well, there's another one at +1. So the zeros of the numerator just equal x-intercepts, don't they? They're just zeros of the function because a fraction equals 0 when its top equals 0. Zeros of the bottom are where the function's undefined, right? Let's try another one. How about that? Tell me, make a prediction about something that's going on with that. Artist, tell me something about that graph. Tell me something about what's going to happen with that graph right there. I want to know some feature about that though. Where do you think we're going to have a vertical asymptote? A vertical asymptote. Is that a new word? Okay. We just talked about that. Notice maybe you weren't really paying attention to that too much. How about somebody else? Kenzie, where are we going to have a vertical asymptote? Let's take that, okay. Where are we going to have a vertical asymptote?
A vertical asymptote?
Yeah.
Isn't that A? Like the vertical?
No,
Isn't that what we're
hang
talking
on.
about?
Won't it be at 1 and -1?
Yeah.
0.
Yeah. How come at 1 and -1?
Because those are your 2 zeros.
Yeah. So if we look at the zeros of the denominator, right? So So let's keep track, zeros of the numerator and zeros of the denominator. So for the denominator, we get zeros at x equals -1, right? That's gonna make that one 0. And x equals 1, that makes that one 0. Okay, Brennan, how about the numerator? Where's the numerator equal 0? At what?
+4.
Where? +4, good. So +4, right? So which ones of those? Justin's telling us that the zeros of the denominator give us vertical asymptotes. You got baseball?
Yeah.
Good luck. What about, what's gonna happen at +4 then? What's gonna happen at +4? Cyrus, what's happening there? If the top is 0 at 4, what's that gonna do to the function? If the numerator is 0 when x equals 4, what does that mean? What does that tell us about the function? What's happening there? Undefined where the top is 0? What's 0 divided by 5? 0. What's 5 divided by 0? Undefined. So one more time. When the top is 0, what's the value of the function going to be? What do you think? Let's look and see.
It crosses the x-axis.
Crosses the x-axis. Good. That's it. Very good. All right.
Your wording is.
So let's try this one. Let's see if this matches what you think is going to happen.
Wait, what?
You just did this math. That's how
Okay, does that make sense? Okay, look at that picture. Look at that picture. Okay, so we have vertical asymptotes, we said, at +1 and -1. That makes sense. X equals -1, let's turn that one on. There it is, there's one asymptote. X equals +1, there's another asymptote, right? Everybody agree? Those match the function. What about at the 0 of the top was at 4? So what's happening at 4? If I do f of 4, what am I going to get back? 0. So right there, at x equals 4, sure enough, there's a 0, an x-intercept. So what are we finding then? This, we can summarize this pretty easily. Zeros of the numerator give us x-intercepts, right? Zeros of the denominator give us vertical asymptotes. Okay. Well, I'm about to throw you a weird curveball here then. What about something like that? Let's make a prediction. Where are the zeros of the numerator? This one's going to be okay. So 1. So we should expect to have an x-intercept there, right? What about the denominator? X equals -5, or what about that one?
Negative.
0. Yeah, if I plug in x equals 0, it makes that factor 0, right? Okay, so we should have 2 vertical asymptotes and 1 x-intercept, right? No big surprise. Okay, no big surprise. That looks like what we thought it would, right? Okay, we had vertical asymptotes at, I got to change these, at -5 and at positive, and at 0, right? Okay, everybody agree? Those match? Okay. If we plug in 1, we get back 0. That makes sense. So right there is an x-intercept. Okay, no big deal. Okay, but what happens if I tweak this so I put an x up here? What does that do? The zeros of the denominator are still the same, aren't they?
Yeah.
Right? What does that do? What are my new zeros of the numerator? I still have 1, but I also have another one. What?
0.
0. Okay, now that's a little odd now. I've got a 0 that appears in both places. So what's going to happen? What do you think? Is it going to be a vertical asymptote, or is it going to be an x-intercept, or is it going to be neither?
I think it's gonna be an x-intercept.
Okay, let's look and see. Okay, it changed everything. Let's do that. Okay, it changed everything. Look what, it did a couple things. How many vertical asymptotes do we have now? Oh, we only have one. We only have one. And where is it?
The left side.
It's the one at -5, isn't it?
Yeah.
Right? So there it is. There's our one x-intercept. But what's going on at 0 then? Let's find out. If I plug 0 into my function, it's undefined. Right? That's kind of weird because it looks like the function is defined at 0, doesn't it? Right? But it's not. I can prove it to you. Let's take this, put a new line up here. Let's say x equals 1. I can drag that line around so it intersects the function. Wherever I drag it, it's going to affect the intersection a little bit, isn't it? Can I make it keep that open? Well, maybe not. But if I drag it around, I can always find an intersection between those two lines, the orange line and the purple curve, right? When I click on it, it gives me an intersection. What happens when I bring it to 0, though? Let's find out what the intersection is. It won't do it. It won't give me an intersection of the curve. How come? Because the function doesn't exist there. Yeah. If I try to find that intersection, it doesn't work. Because what's going on now is we've generated what we call a hole in the function. All right, so if we want to see what's going on at 0, we know it's not defined. I would have to do something like this. This is how we draw it in math. We'll put an open circle there, meaning there's a hole in the function there, right? The function doesn't exist. There's not a vertical asymptote, but because we have this factor that has a 0 on both the top and the bottom, it creates a hole in the function. What do you think is going to happen if we algebraically, one last thing, then this will be it for today. We'll hang in there for a few more minutes. Algebraically, Ariel, what could I do to this function? Is there a common factor that I could cancel in the top and the bottom? On the top, I've got x times the quantity x minus 1. On the bottom, I've got x plus 5 times x. Is there a common factor there?
X.
X, yeah. I should be able to cancel out the x algebraically, right? Okay, let's do that. Let's see what happens if I graph that new function. This is good. Just trust me, you'll like this. If you don't, you just got to make yourself like this. Sometimes in life, you just got to make things interesting. So I'm going to graph, this time I'm just going to graph x minus 1 over x plus 5, because if I cancel the x's, that's what's left, right? Okay, well look at the two functions. They look identical, don't they? Right? So if I turn this one off, watch what happens. If I turn this one off, it looks the same. I turn that one on and turn this one off. They completely overlap, don't they? Right? Let's turn off the original one. What happens if I define I'm going to call this g of x. Okay, if I evaluate g of x at 0, so let's find g of 0, it gives me a value. What did I just do? If I try to evaluate f of 0, it's undefined. But when I cancel the x's out, what did I do to that hole in the function?
You filled it.
I filled it in. That's what we did. We filled in the hole. When I have, so let's summarize this, right? If I've got zeros of the numerator that are not zeros of the denominator, those are x-intercepts. If I have zeros of the denominator that are not zeros of the numerator, it's a vertical asymptote. But if I have a number that's a zero of both the top and the bottom at the same time, what is it?
Asymptote.
It's a hole. It's undefined, but it's a hole in the function. That's all it is. It's one little, it's a point discontinuity because it's just one little pixel is all it is. It's one point that's missing. That's a lot different than a vertical asymptote. We call that an infinite discontinuity because it's huge. The function has been massively torn apart, right? But this is just one little hole in the function. Okay, and you can fill it in, and we do this in calculus. You can fill it in by just dividing away the, canceling the two factors. Okay? All right, that's good. There's an assignment you can grab.
We have 5 minutes.
I know, but you can grab this paper assignment. Yeah, I know, paper, that's unusual. Grab that paper assignment, the 8.2 paper assignment. And you're not gonna be able to do a ton of that today, but after tomorrow you'll be able to do more.
Both of these?
Just that one, you got your hand on, the right one, your right hand, that one, yep. 8.2 paper assignment.
This was